We've been studying first-order linear systems, homogeneous linear systems, so they have this form, x prime equals ax. Now here A is a constant coefficient matrix, so a matrix made up of, obviously, constants. Now, contrast that with a first-order linear scalar differential equation. And we've seen these a long time ago, and it's just a simple first-order linear equation. Now they look very, very similar. Other than one being a vector and one being just a function, they are almost identical. So can we solve them the same way? And what I mean by that is, let's talk about integrating factors. So if we take a look at the scalar equation, remember that if we reorganize this scalar equation and we set it equal to 0, the term in front of the x allows us to determine something called the integrating factor. Now, the integrating factor we get when we take the natural exponential and raise it to the antiderivative of that term. So here we'll get e to the minus at. If we were to multiply both sides of this equation by that e to the minus at by the integrating factor, obviously on the right we'll get a 0. The point of the integrating factor is that it will turn this function, it will turn this into a perfect derivative, the function times the integrating factor. And that allows us to take an antiderivative and we'll get a constant and we'll be able to figure out the function, c e to the at. So it's no surprise that it's an exponential function. Now if we're given initial conditions, so let's say x of t naught is some constant vector, or let's even simplify things and set it equal to 0. We can always redefine time. Then x of 0 is x naught, x naught, just a scalar here, and that would just be c, because we'll have an e to the 0. So c would be x naught, and voila, we'd get our function. It would just be x naught e to the at. So a natural question, is there an integrating factor for systems? And in order to answer that question, we need to have some sort of version of an exponential. Now, what we would need is we would need to be able to somehow take an exponential, raise it to a matrix, and then take an antiderivative. And if we could do that and we could have a matrix, which is a constant, we would just antidifferentiate it, then we could do this. But how on earth do we do that, right? And the answer is always just define it. Why not? Let's create this thing. Let's call this the matrix exponential. So let's define something called the matrix exponential. And how are we going to do this? What would be a sensible way of doing it? Well, from calculus, you learn about Maclaurin series. You learn about Taylor functions, Maclaurin series expansions, all that kind of stuff. And there's a Maclaurin series for e to the x. So it's given as a power series representation. So just like this. And if you expand it, it would be 1x squared over 2 factorial, x cubed over 3 factorial, so on and so forth. Now, in calculus, this is a result of a theorem. This is the thing that you get popping out of doing a bunch of work, and the exponential function is defined a little bit differently. But later on in other places in math, we take this and we use it as a tool for defining things. And we are going to use this as the definition for a matrix exponential. Why? So that we can introduce an integrating factor. Now, this is a general result. Whenever you want to put something strange into an exponential, you use this Maclaurin series definition to allow you to do it. So we are going to define the matrix exponential as this power series. And it will be given by this. And in terms of the expanded version, it would be the identity matrix, a squared over 2 factorial, 1/3 factorial a cubed, and so on and so forth. Now, what's important here is that A has to be a square matrix in order for you to define all of these powers. Now, you can go ahead, and I'm not going to do this, but you can prove a whole bunch of these things. So if you wanted to, you could weight that matrix here, the constant matrix, by a scalar that we're going to call t. And in this case, when you expand it all out, you would just follow the same definition as above. And then you would get these other properties. So again, mathematicians have gone through and thought about this and used the definition, and you can almost think of it very simply as term by term. But you should be able to see that if we were to take the derivative here, a similar thing to the chain rule would apply, and we would get e to the something times the derivative of the something. So this is going to end up giving us a e to the ta. Now we have to be really careful here. This matrix exponential, this produces a new matrix. So this object right here is in fact a matrix. It's an n by n matrix. Just like this is an n by n matrix. And this term right here will also be a matrix. So we have to be slightly careful when we multiply things. We'll have a matrix times another matrix. So you might say, oh, does it matter what order we put that multiplication in? Well, luckily it doesn't, because you can prove that the order of this multiplication does not matter. It commutes. Finally, the other property that you can prove is that if you wanted to take the inverse of this exponential matrix, it would be the same as putting a negative scalar t in the front there. Now note, this is not division, right? A -1 power is not division here because it's not defined for matrices. There's no such thing as matrix division. That's what the inverse does. So if you go ahead and you define these properties, now it lets you tackle the first order homogeneous system just like we would before. Now we can use an integrating factor. So we can use this integrating factor approach. And what I mean by that is we're going to go ahead and we're now going to talk about this initial value problem. We'll have our a vector system, x prime equals this ax, and we'll take some initial condition. Now, we'll define this as we did for the scalar system. We'll move everything over. We'll have a 0. And the integrating factor is going to be the exponential with this integral, and we're going to end up getting e to the minus ta. That'll be our integrating factor. So we're going to be careful, and we're going to multiply everything on the left because we're dealing with vectors and matrices multiplying vectors. And when we do so, we have to pay attention to the order. This will give us the 0 vector as before. And the whole purpose of doing this is because this will end up being the product of the derivative of the product of this integrating factor times x. Just like before. And when we go ahead and we take the antiderivative over there is going to give us a constant vector. And normally we would divide through by this exponential function, but now instead what we need to do is multiply by its inverse up here. And so the inverse in this particular case is going to be e to the ta. So there's an e to the ta there. We are going to multiply through. This is going to give us the identity. What we'll have is x of t is e to the ta times this constant vector. And again, remember, it matters which order we multiply things in. And this is great. This is just like before. This looks identical to the problem I solved at the onset. If that's 0, we got x of t was just c e to the at. They look the same. That's kind of neat. Now, it isn't really a surprise because there's a great deal of symmetry here, and we're going to exploit this symmetry throughout the whole thing. Now, if I have initial conditions, I can take my solution and raise it to the power of 0, and this is just going to tell me that my constant is given by that. So, we have successfully solved this linear system by using a matrix exponential. In fact, we defined a matrix exponential and used it to come up with a solution, at least a formula for the solution. Now, there's a bit of a headache because it's difficult to work with. How do I find this, or how do I compute this? Right? The definition is difficult to use because it has these power series. And there's a lot of them, infinitely many. So there's another approach. We can compare this to how we normally solved a first-order system. If I had given this first-order system a little while ago, we know that the solution x of t is a linear combination of all of these fundamental solutions. If it's an n by n system, we have to have n of these fundamental solutions. And that means that we can write this system as a matrix vector product. And that means we can define this thing here to be a capital X of t. This is going to be something called the fundamental matrix, because it's a matrix that holds all the fundamental solutions. And this will be a constant vector. So we'll have this x of t times c. And if we wanted to actually go ahead and apply it, if we have these initial conditions, that means we would take that fundamental solution, x of 0 and c, and that should be equal to x naught. And because this is a fundamental matrix, we can invert it. So if I were to take both sides and multiply by the inverse of this thing, I would be able to get an expression for c. It would just be the inverse of this fundamental matrix at 0. And then we put it all together. And when we put it all together, here's what we get. We'll get this x of t, the inverse of the fundamental matrix at 0. That's what we would get by solving the system in the normal way. Why am I doing all of this? Because up here, I solved the system by using the matrix exponential. And if I compare them, here's what I'd find. That I'd have the matrix exponential times this x naught. So I'm hoping that you can see that from above here, it's a very easy way for us to determine the matrix exponential. And here's the point. If we have to define this matrix exponential, e to the ta, we use this power series version. This is the strict definition. And if we wanted to calculate this just by providing a matrix A, we would go ahead and we would do this. It would be cumbersome. It would be tricky to do because we'd have to compute many of these these products and then a power series. But if we actually just want to compute this matrix exponential for a system of DEs, then we're in luck. Then all we need to do is just calculate the fundamental matrix and then form this inverse. This is definitely easier. Now again, it only applies in the context for a homogeneous system like this, but we won't care because that's exactly the context we want to be in. So now that we've got this matrix exponential idea defined, we have a simple way of computing it. It requires us to know the fundamental basis. But once we've got that, then we are set and we can go ahead and calculate solutions to non-homogeneous problems.